Okay, so this is the video where I'm going to prove the pigeonhole principle. So this is the proof of the pigeonhole. All right, so this is the idea here. So let me restate the theorem. So let me just state it in words first. So it's that if you have more pigeons than you have holes, you can't stuff the pigeons in the holes. If you have more nerds than lockers, you can't stuff all the nerds in the lockers without trying to double them up. Okay, so this is the pigeonhole principle. Sorry about my handwriting. Okay, so if n is greater than n is greater than r, there is no. It's a really stupid statement. There is no injection, but here f nn to nr. Okay, so the notation is that again we're using this thing m1 m, so 1 2 all the way up to m. Okay, so this is the idea here, and so to do this so like this is one of these things that's like, okay, it's obvious, but because we're mathematicians and we're careful about things, we have to take our time and do it right. Okay, so all right, so I'm gonna develop enough to prove this. So I gave you an exercise on the homework, and I'm gonna state it again. So here's the exercise. This is the exercise we need. Okay, so there's two parts. So first part says if A and B have the same cardinality, so that there's a bijection between, or let's say A and C, and let's say B is in bijection with D, so that there's a bijection between these, then the products have the same cardinality. A cross B is in bijection with C cross D. Okay, so if A is in bijection with C and B is in bijection with D, then the product of A and B is in bijection with the product of C and D. Okay. Two, the second thing that we want to show is that if A and B are disjoint, these are sets. Okay, all this is about sets. And C and D just are disjoint. A has the same cardinality as B, and A has the same cardinality as C, and B has the same cardinality as D. Then what we'll have is that A union B is isomorphic to C union D. So they have the same cardinality. Okay, so these are the two things that we do. So the ideas. So for the first part, you're given, F. So this bijection here, G bijection from B to D. So I'm writing this little tilde here to show an isomorphism. Then H, of AB looks like F of A, G of B. Okay, and so this is an element of C cross D, and then you need to check that it's a bijection. So you check the rest. Okay, the other part here is that so you define, so I'll use the same notation as before. So you do H of X. Okay, so then you do something like this is F of X if X is an element of A, and you do G of X if X is an element of B. So like where F and G are bijections as above. Jections as above, as in 1. Okay, so that's the idea. And so you just gotta kind of fill that out to do the rest of this thing, okay? And this is something silly that we have to do, okay, but it's something that we have to do. Okay, so let's recall briefly what finite sets are and infinite sets are, okay? So, and then the other thing that I needed to tell you was how non-finite and infinite sets work, okay? So the definition. So a set S is finite if there exists some n, and so now I'm going to say a non-negative integer such that S is in bijection with n sub n. Okay. So let me make a remark on the notation. So for n is equal to 0, we're going to use n sub 0 to be the empty set here. Okay. Also, for n greater than 0, n sub n is just the set 1, 2, ... all the way up to n. All right. So we're using this notation again. All right, and so one of our goals, one goal thing that I owe you, thing we need to do before we get into this is so I'm gonna start over. The good thing about doing this on video is that I can take a mulligan here. Is equivalent to. I didn't like what I started, but the lemma is still the same. Let me just state what I was going to do. Definition of infinite. So if. And so this means that it's in bijection with a proper subset. Cardinality n, and x is not an element of S. Then when we join proper this set here, this is going to be cardinality n to the n plus 1. But we'll deal with this a little bit later. So I haven't said that yet. I just wanted to mention. It's going to be n plus 1. Okay. Okay. So cardinality is just going to be equal to n plus 1. All right. Okay. So here's the proof. Okay, and I said it by induction, but I don't think we actually need to do this by induction. So, by definition, so this being cardinality n, S is in bijection, so there's a bijection with n sub n. So this is the okay, that's just the definition of what this means, and then. So also, n plus 1, so this is n union n plus 1 like this. Also, we have that x is, this is in bijection with n plus 1. So, so we have this, so we are in the setup of the lemma. Setup of the lemma, the previous lemma. So A is, well, it's one of the things where we take the disjoint unions. A is equal to S, B is equal to X, C is equal to n sub n, and D is equal to n plus 1. So the bijection between those two things is obvious. So then we have, so we have A union B, this is equal to, so we get a bijection. A union B is S union the single, it's an X, and this goes to C union D. This is a bijection, and this is N union n plus 1, and this is this set here. So this shows that the cardinality of S union this element that's not in there is n to the n plus 1, like so. Okay, so the cardinality increases when you adjoin another element. Okay. All right, so what I wanted to say is that, so unlike, so a remark, so this is distinct, from infinite sets. So in infinite sets, you can adjoin a single new element, and so this is so you can adjoin a single set, or a single element to a set, and by the Hilbert Hotel, where you shift every so the Hilbert Hotel is where you have an infinite number of guests, or countably infinite number of guests, and to always accommodate a new person, you shift every hotel guest down one room, and then you put them in the first room that's left over. Okay, this is distinct from infinite sets where we can always accommodate one more element. All right. So now I kind of need to prove a bunch of different lemmas. Okay. So let's do a bunch of different things. So now I'm going to move from this n sub n element set to this. Well, okay. Let me just continue. So and I'm going to use the definition of finite. So lemma. Okay. So let me just kind of write them out. So let me write it as 1. So every subset of here. Okay, 2, every subset of a finite set is finite. 3, so if A and B are finite disjoint sets, then A union B is finite, and the cardinality is just the sum of the cardinalities. Okay, 4 is that if, not necessarily finite, if A and B are disjoint, or if A and B are finite sets, not necessarily disjoint. So then A union B is finite. Okay, and then let's do one more, is that if A1 through AN are finite, these are finite sets, then the union of all of them is finite. And the last one we have is that so for all r in the natural numbers and all x in n sub r, if we just remove an element here, then it's isomorphic to the, so any so if you remove an element from an R element set, then it's going to be an n minus R element set. Okay, so these are the things we need to prove. Okay, and so so why are we doing all this? So why? Okay, so we need all this. So we need this. This for the pigeonhole principle, and this is what I said, that this was the boring part. Of doing, like, this is kind of like the dirty work of playing with cardinality. All right, so let me just go through these. Then I guess they're kind of good to see some proofs, and I think everyone should be able to do these. Okay, so let's do the proof of 2. Or proof of 1, sorry. Okay, so so this is saying that every subset of NM is finite. All right. So proof. Okay, so the proof is by induction. All right. Okay, so okay, so let's do the case m is equal to 0. So nm, so then n0 is the empty set, and clearly every subset of here is finite. Clearly every subset is finite. Okay, so the inductive step. Okay, so okay, so suppose the theorem is true for subsets of an n, and prove it for n plus 1. Okay, so we're going to let A be a subset of n plus 1. Okay, and then there's two cases. Okay, so there's two cases. This is that A is equal to A set minus n plus 1. And so the other one is that A is equal to A set minus n plus 1 union n plus 1. Okay, so we'll call this case 1, and this is case 2. Okay, in case 1, so in case 1, A is a subset of n, and the result follows, so the result follows by inductive hypothesis. In case 2, so A set minus n plus 1, this thing's a subset of n, and so this is, and so this set is finite by inductive hypothesis. So then, and we'll say that so that there exists some r in the natural numbers, i.e. there exists some r in the natural numbers such that A set minus n plus 1. Here, this is isomorphic to, there's a map F to n sub r. Okay, then using this, we use that the lemma that we had before. This is A here, union, and this guy here is n r union r plus 1, like this. So by the lemma, we have a bijection like so. Okay, because we have these two isomorphic singleton sets, and then by inductive hypothesis we have the isomorphism between these two things, and then this whole thing here is n r plus 1. All right, and so these guys are in bijection. Okay. All right. Okay, so this is the proof of 1. Okay, so let's prove the next step. Okay, so proof of 2. Okay, so this one also is not very difficult. It's that every subset of a finite set is finite. So sorry. So let's see. So we showed that every subset of n is let's see. Nm is finite. So we know every subset of a finite set is finite. So every subset of a finite set is finite. All right. So let A be a finite set. So let S be a finite set. And let A prime or A be a subset of S. So by definition of S being finite, so there exists some map to n sub n. Okay, some bijection. Okay, and also, so this gives f restricted to A, a bijection from A to f of A subset of n. Okay, so then this is a bijection onto its image, and so by the previous lemma, for the previous part, okay, f of A here is isomorphic to nr for some r less than or equal to n. Okay, and so that means there exists a bijection from this set to this set. Okay, and so so the composition of bijections is a bijection. Okay, since the composition of bijections is a bijection, we get a map from A to f of A. Okay, so this was the map f restricted to A, and then we get a map from f of A to n sub r. And so this map was given from the previous lemma. And so this composition gives the bijection. Okay, so this thing here, let me just say what these things are again. So this is given by the previous lemma, previous part. And then this one here is given, so this one's given by that the restrictions of bijections are bijective onto their image. And then we get this third one, is that the composition, so this one here, is that the composition of bijections is a bijection. A bijection. Okay, now I'm going to continue. So we did 1 here, we did 2, now we're doing 3. If A and B are finite disjoint sets, and A and B is finite, then we have the following, that we have these two things, okay? Okay, so let's do the proof of this last one. So the proof of 3. Okay, so this thing okay, so this is what we're trying to prove. Okay, so Okay, so let's let A and B be finite sets. Okay, so then is a finite disjoint. Okay, so we'll have, so we just write it out. So so there's a bijection here to n sub A, and there's a bijection here, let's write it like this, so to n sub B. Okay, and then this can be, there's also a bijection from n sub B to the following, to here we can write it as A plus 1, A plus 2, A plus B, like this. Okay, and so we'll call this, I don't know, what do we want to call this? We'll call this n sub A plus B set minus n sub B, or set minus n sub A. Okay, so that's what this thing is. That's what this set is. Okay, and so we apply our lemma again. Our lemma about bijections of disjoint unions. Okay, and what does that give us? So we have A union B. This is in bijection by the lemma with these two disjoint sets, NA union NA plus B union NA, or sorry, set minus NA. So these numbers, and then this is actually equal to NA plus B. Okay, and this proves that the cardinality of A union B is equal to A plus B. Okay, which was the cardinality of A and the cardinality of B by these two things. Okay, so let's do the proof of 4 now. Proof of 4 was that when A and B were not necessarily disjoint. Okay, here. Okay, so the proof of 4. Okay, suppose A and B are finite sets. Okay, so then, well, A union B, so any subset of a finite set is finite. So A union B is equal to A union B set minus A. Okay, and this is equal to, this is the union, this is a union of finite disjoint sets. Okay, so and hence by the lemma, by the previous lemma, is finite. Oh, excuse me. So why do we know that this one's finite? Because this is the complement. This is a subset of a finite set. B is finite, and any subset of a finite set is finite. And that's what we already showed that one. Okay. So proof of 5. 5 was now not just the union of two sets, but the union of arbitrarily many finite sets, but a finite number of finite sets. Okay. So let's do the proof of 5. Okay, so proof of 5. Okay, so we will show that that A1, that for every n and every A1 to AN finite sets, that this union is finite. Okay, so the proof is by induction. Okay, the base case. Okay, the base case will be n is equal to 1. A1 is a given finite set. Is given, so we're done. Okay, so it's just we have one union here. Okay, let's do the inductive step. Okay, so so suppose it's true. So here we have A1 union A2 union here, union AN. So this is finite by inductive hypothesis. So we're supposing it's true for n minus 1, and we're proving it for n. Okay, and so then we have this thing A2. Let me just write it out. Union AN is equal to A1 union B. So it's a union of two finite sets, and hence finite. All right, so now we have the union of finite sets, and this is finite. Okay, so that gives us, so since we proved the base case and we proved the inductive step, we're done. Okay. Okay, so now we need to prove the last part. Okay, so the last part is that says the following. Proof of 7. Okay, and 7 said that, let's go back. 7 says that if you remove a point, it's the same thing as if we were going to do n r minus 1. Okay. Okay. So we will show nr okay, so the proof, okay, so by induction well, I mean, I guess we don't need to really do induction here. Let's see. So there's just like you can even rearrange the terms here. So, so if okay. So let's do the case if x is equal to r, then nr minus r is equal to nr minus 1. Okay, so that's clearly, so we are done. So since it's actually equal to it, so the bijection is just the identity. Okay. If x is not equal to r, then what do we have? So then, so then we have that, so then we have that nr set minus r here. Maybe this is cheating a little bit. So, so we have two disjoint sets here. So we have, this is nr, okay? Okay, so now we have two finite disjoint sets. This is the cardinality of nr here, okay, plus the cardinality of this thing here is equal to this cardinality. Okay, so this tells us that the cardinality plus the cardinality here, well, is equal to n, the cardinality here. This is R. Okay, and then let me just copy this over. So this tells us, I'll just do it on this page. So this is the cardinality of n, R without 1. So this is equal to plus 1 is equal to R. So this tells us that the cardinality of this thing is equal to R minus 1. Okay, and then by definition, so by the definition of cardinality, this proves that here it's in bijection with this set here. Okay, then there's a couple ways to do this one. Okay. All right, so we did all this work proving these lemmas, and now we are prepared to prove the pigeonhole principle. Okay, so let me just restate this. So theorem. So the pigeonhole principle if n is bigger than r, then there does not exist an injection here from n sub n to n sub r. All right, proof. Okay, so suppose the pigeonhole principle. So okay, so let's do this proof by induction here. Okay, so the proof is by induction. On n. Okay, so if n is equal to 2, then we're looking for maps from the set 1, 2 to the set 1. Okay, and this is clearly not injective, right? Is never injective. Okay, because everything maps to 1. There's only one thing to map to. Okay, so let's do the inductive step. Okay, suppose that it holds for n and prove it for n plus 1. Okay, so let me just say what the precise statement is. Okay, so the statement is that for all r less than n, greater than or equal to 1, and all f, where f is a function from here to here, is not a bijection. So baked into the statement here is that it's for all r less than n, and this is only on one free variable. The one single free variable is n. Okay. Okay. So suppose now that f is a map here to nr with r less than n. Okay, and so and we can suppose that r is bigger than or equal to 2, or is bigger than 1, since the case r equal to 1 is clear. Okay, let me just say what that means is that when r is equal to 1, we'll have a map to a single point. And a map to a single point can never be an injection, since there's many points here and they all have to have the same image. Okay, so we can check that one. Okay, so okay, so so now we consider the map here, f restricted to n sub n. Okay, and by definition, since this set here is the union of this plus a single element, we may write it as here to n sub r. So this is at least 2. That's why we suppose this set minus the set of f of n plus 1. Okay, and since we're removing a single element, this could have landed anywhere in here. By the lemma, this is isomorphic to n sub r minus 1, and this is still a positive thing. So this was by the last part of the lemma. And maybe I can scroll back here. Oh, let me go back. The last part of the lemma here is this thing here. So if we remove 1, then we get this thing. Okay. Okay, and so so we have this thing, and so by inductive hypothesis, this map is not injective. Is not injective. All right. Okay, and so that's the proof of the pigeonhole principle. So if you let me just say one more thing while we're done, is that if you have a map and it's and one of its restrictions is not injective, the map itself cannot be injective. I mean, unless you're restricting to the empty set or something, but that's stupid. Okay, this is a non-empty thing. Okay, so that's the proof of the pigeonhole principle. We just had to build all those lemmas and up to prove this, and then we had to check so we had to check all this crap. We had to check that, where is it? Okay, we had to do so much, right? We had to show that, subsets of these truncated natural number sets are finite, and every subset of finite set is finite, and the union of finite set is finite, and then stuff like that. Okay, so that's what the idea of proving the pigeonhole principle was all about. Okay, now we can use this to talk about the difference between infinity and finite sets, now that we have this pigeonhole principle. All right, I'm going to do that video now.